Okay, so this is going to be the last example of concavity and points of inflection. This one's a little bit more complicated because this is a rational function. So you probably should practice, take the derivative, and then find the second derivative by hand. Um, that's going to take a while. So I went to Wolfram Alpha, and there's something I want you to see here. First of all, here's the first derivative. That's not going to really do us much because we're talking about points of inflection. Um, so if you're going to go right to Wolfram Alpha, you would just go to second derivative. But here's what I want you to see. The second derivative, they give you this really kind of unsimplified version, and I'll show you on the screen. Oh, there's me again. Hey. Um, Here's what they show you. So you're going to have to scroll down a little bit to look at an alternate form. And this is the alternate form right here is the one that's going to be very useful to us. So I'm going to go back and show you that. That's the alternate form. This is the second derivative that we're going to be taking care of here. So this is f prime of x, f double prime of x. And it is very simple. Um, the second derivative never equals zero because 6 is on top and 6 doesn't equal zero. So there's no place where this equals zero. The bottom does equal zero at where 2x plus 1 equals zero. And if you solve that, you get x equals negative 1/2. Here's the thing, though. You can't call that a possible point of inflection because it's not going to be a point of inflection because look at the original function. The original function, the bottom is 0 at negative 1/2, which means x equals negative 1/2 is really just a vertical asymptote. But here's the important thing about that. We know we're not going to have any points of inflection because there's no possible points of inflection. But this can still change concavity at a vertical asymptote. Anything can happen at a vertical asymptote, as you may have remembered from last section, mins and maxes. So when you try to figure out where this function changes concavity, you're just going to have to use the vertical asymptotes as if they were possible points of inflection. So I'm going to set up my chart the same way. But the negative 1/2, instead of being a possible point of inflection, is just a vertical asymptote. So I'm going to label it as such. And now nothing changes. So now we do the same thing, set up our intervals. The derivative, second derivative at some place in this interval, say negative, you can use any number, negative 100. If you plug that into the second derivative, notice the second derivative is negative right here. So this is negative. 6 is always positive. Over, if you plug in a negative 100 here, you're going to get a negative number cubed, which is negative. So you get a negative, positive over negative, which is a negative times a negative, which is positive. Negative, negative, which means we're concave up in this interval. The next interval, we're going to plug in anything after negative 1/2. 0 is the easiest. The second derivative now, we have a negative. 6 is positive. And obviously 2 times 0 plus 1 is positive. So we're going to have a negative positive over positive, which is a negative times a positive, which is negative, which means concave down. So this function is concave up on the interval negative infinity to negative 1/2 and concave down from negative 1/2 to infinity. Now, we're going to check that with a graph. If you don't have a graphing calculator, go to Desmos. Everybody can get the Desmos. So I want to show you the graph from Desmos. I just type it in, and then here's the graph. You can see that there is an asymptote at around -1/2, and you can see this is concave up from here to here, and this side is concave down, which we determined. So this is just a good check. That's it.